Hi again, everyone. Chris Tisdell here again. Thank you for tuning in. In this presentation, we're going to continue our series on matrices. And in particular, I'm going to do an example where we use matrices to see if two planes intersect. So this is a nice connection between matrices, linear systems, and a little bit of geometry. So let me share my screen with you and we can have a look at the example. Okay, find the intersection of the planes. Okay, so you would sort of judge from the nature of the question that they do intersect. Now, planes can intersect in a number of different ways. They can intersect along a common line, or they can lie on top of each other, so they intersect everywhere. So which one is it? Well, we're going to use matrices to shine some light on this subject. Now we're working in, say, three-dimensional space here. So by this, we just mean the vectors x, y, z. And what the question is asking us is, determine the values of lambda 1, lambda 2, mu 1 and mu 2 such that these two equations are equal. Okay, so to do that, set the equations equal to obtain the following. Okay, so let's 1, 2, 1 plus lambda 1, 1, 1, negative 1 plus this equals 0, 1, 0 plus this. So here lambda 1, lambda 2, mu 1 and mu 2 are sort of parameters, they're unknowns in this case. 1, 4, 6. All right, all right, let me just zoom out a little bit. Okay, all right, so let's try to solve this linear system. Okay, so this is written now sort of as a vector form. So let's set up an augmented matrix. First of all, we want to get all the constant vectors on one side and lambda 1, lambda 2, mu 1, mu 2 on the other side. Okay, so what I'm going to do, I'm going to take this to this side and these two to that side. Okay, so let's rearrange. All right, so what are we going to get? That's going to go over here. So I'm going to get 1, 1 and 1. Okay. And on the other side, I'm going to get something like let's bring this over here. Oh, yeah, let's bring that over there and we'll write it this way. 1, 3, 4. 1, 4, 6. Let's bring that over there. I'll get negative 1, negative 1, 1, negative 1, negative 3, negative 5. And just to be really definite, I'll put the mu 1 here, the mu 2 here, the lambda 1 here, and the lambda 2 here. Okay? Okay, so let's write this as an augmented matrix. And then we're all ready to start. All right, so 1, 1, negative 1, negative 1, 1, 3, 4, negative 1, negative 3, 1, 4, 6, 1, negative 5, 1. Okay. All right, so what do we do now? Well, we want to row reduce this matrix down to something else, okay? And for that, what we usually do is we choose a pivot. Now, the pivot entry is up here. In this case, it's a 1, and it's in the top left-hand corner, which is good, okay? The way I sort of set that equation up, it was easy to do so. Now, once you've chosen our pivot, what we want to do is do some row operations and row reduce the matrix to what's called a row echelon form. The first step is to look under the 1 and make this a 0 and make this a 0. So how do we do that? Well, row 2 is going to become row 2 minus 3 times row 1, and row 4 is going to become row 4 minus 4 times row 1. So let's write those down. Okay, so let's see. Now, it's easy to make a mistake with these sorts of row operations, so let's just be nice and careful now. Okay, so the top row is definitely not going to change. All right, so 3 minus 3 times 1 is 0. 4 minus 3 times 1, that's 1. Negative 1 minus 3 times negative 1, so that's negative 1 plus 3, so that'll be 2. Negative 3 minus 3 times negative 1, so that's negative 3 plus 3. 1 minus 3, and that'll become 0. 6 minus 4, 1 minus negative 4 times 1. Basically, this is 1 plus 4, so that'll be 5. Negative 5 plus 1, plus 4, negative 1, and 1 minus 4, negative 3. Okay. All right, so now what? Well, now we move on to the submatrix. Okay. Basically, we repeat the process just on this matrix here. So this, we've already got a pivot, and it's in the top left-hand corner of the submatrix. So we want to get everything underneath that 1 to be 0. So what we're going to do is do row 3 equals row 3 minus 2 row 2. So what's going to happen then? Okay, well, top row is not going to change. Okay, and row 2 is not going to change. Okay, so that'll become 0. 5 minus 2 times 2, 5 minus 4, that's 1. Negative 1, well, that's going to be 0. And negative 3 minus 2 times negative 2, so that's negative 3 plus 4. That'll be something like 1. Okay. Okay, so we're almost finished now. Okay, so let's have a look at the bottom row. Okay, so this is basically saying, so that's the row associated with mu1, that's the row associated with mu2, lambda 1, and lambda 2. So what does this bottom row say? It says, okay, first of all, it says 1 lambda 1 minus lambda 2 equals 1. And similarly for the other rows, you can form equations. But you'll see that every column is leading. This column contains the first entry of this row. This column contains the first entry of this row. This column contains the first entry of this row. But this one doesn't. This is a non-leading column. Okay, so what that means, and this is non-leading. So what that means is there's an infinite number of solutions. Okay. And the way we proceed is that, okay, that's associated with the lambda 2 variable. So let's make lambda 2 some sort of parameter, okay? So since column 4 is non-leading, let lambda 2 be a parameter. Let's say, let's just make it lambda. All right, and what we'll do is we'll use back substitution and get everything else in terms of this lambda. So we'll get lambda 1, mu 2, and mu 1 in terms of this lambda. All right. So R4 yields, okay, so R4 says 1 lambda 1 minus lambda 2 equals 1. Okay, so that's lambda 1 minus lambda 2 equals 1. So replace lambda 2 with lambda and get lambda 1 as a subject. 1 plus lambda. Great. All right. So let's keep going now. We've got lambda 2, lambda 1. Let's go back and get mu 2 and mu 1. Okay. So let's look at row 2. Oh, sorry. Did I say row 4? No, row 3. That's row 3. Row 2 now. All right. So what does row 2 tell us? Row 2 tells us 1 mu 2 plus 2 mu 1 plus 0 mu 2 equals -2. So that is mu 2 plus 2 lambda 1 plus 0 lambda 2 equals -2. Okay, so I know what lambda 1 is in terms of lambda. It's right there. It's that. And I can simplify that, -4 minus 2 lambda. And the last thing we want to get is lambda 1. So from this, again, from this matrix, it says lambda 1 plus, mu 1 is what we want. Mu 1 plus mu 2 minus lambda 1 minus lambda 2 equals 1. Okay, so we can use that then. Okay. So we've got mu 1 plus mu 2 minus lambda 1 minus lambda 2 equals 1. All right, so let's make mu 1 the subject. Okay, mu 2 is that. Plus lambda 1. Lambda 1's that. Plus lambda 2, which is that. Okay, so now all we need to do is simplify. Hopefully this simplifies well. We've got 1 plus 4 plus 1. And then we've got positive 2 lambda plus lambda plus lambda plus 4 lambda. Okay. So there we go. All right, so that's all our stuff. Okay, so let's find the intersection then. We can write these things as the equation of a line, okay? So basically all you want to do is you can go to either of these. Let's say go up here, right? We can replace lambda 1 and lambda 2 with these particular values, and then we'll get the equation of a line, okay? So let's do that. So let's give this a label, say star. Okay. So I'm going to call this first one star. So sub lambda 2 equals lambda, and lambda 1 equals 1 plus lambda into star to obtain the following. Okay. So replace lambda 1 with that, lambda 2 with that, and then it'll be a simplification. Okay, and all we need to do is put the constant vectors together. So if I expand that, it'll be this plus 1 times all of that, so I'll get 2, 3, and 0. And then I've got a common factor of lambda for the other vectors, and I can just add this up. So it'll be 2, 4, and 4. Okay. So this then is the equation of the line of intersection in a vector parametric form. Okay, there it is. Whew. Okay, what did you think? It was quite a long and convoluted problem, but the principles aim to link your matrices with your geometry, with your linear systems. Okay, so I probably, if you were being critical of this presentation, you'd say, well, you didn't need to calculate mu1 and mu2. Well, I just thought I would. Okay. Okay, so there is your equation for your line of intersection. So what do you think? Hopefully you've got the idea of the process now. Take the problem, set the two equations equal, put it in an augmented matrix form, row reduce it to a row echelon form, and then you make some conclusions. We just did a bit of back substitution. If you have any comments, any questions, love to hear them. Thanks for watching. See you later. Bye.